Thank you for coming to my talk. So the title of my talk is Information Geometric and Optimal Transport Framework for Gaussian Processes. So yesterday we saw a lot of applications oriented work, but I'm sorry, this talk is actually not applications oriented. It's actually entirely theoretical. So I'm sorry if that's too much math, but I would not cover everything. I wouldn't cover as much as I can, but not everything. Okay. Okay, so the outline of the talk is I will be talking about the generalization of the following geometrical structures for probability measures on Euclidean space, the Fisher-Rao metric and distance, and the optimal transport distances to the infinite dimensional probability measures, and with the concrete results for the infinite dimensional Gaussian measures and Gaussian processes. Because when we deal with Gaussian processes, we are really dealing with, especially for Gaussian processes, with square integrable paths, and we are really dealing with Gaussian. They are induced by Gaussian measures on an infinite dimensional Hilbert. The motivation for the studying of the infinite dimensional setting because it's really motivated by the Gaussian processes. And so I'm talking about two things, the Fisher-Rao metric and distance coming from information geometry, which is a very big field in Japan. As the founder Shunichi Amari, which is who is very famous, who is for a long time actually worked at RIKEN. And we're also talking about the second direction is optimal transport, which is now a very big direction in machine learning. So what are the main mathematical theories and techniques? So here we need to explore the interplay of the theory and techniques from the various mathematical fields. So operator theory, the positive definite operators. This is the kind of the generalization of the positive definite matrices to the infinite dimensional setting of Hilbert space operators. We'll be utilizing Riemannian geometry in the infinite dimensional setting also, because everything we deal with will be infinite dimensional. And the theory of Gaussian measures on Hilbert space and Gaussian processes. And we also utilize the reproducing Hilbert space or RKHM methodology for the analysis of the sample complexity, along with the probability theory on Banach and Hilbert spaces. So actually it involves various different fields in mathematics. So the motivation for the studying of geometrical structures for Gaussian measures and the symmetric positive definite matrices, so SPD matrices, they play a very central role in statistics and probability in machine learning, or they also have numerous practical applications. So there are a lot of applications in brain imaging, in computer vision, in radar signal processing, in brain-computer interface, and so on. So this is where we apply, it comes from the covariance representation of data in these fields. So for this, in brain imaging computers, we have the methodology of representing an image, for example, by a covariance matrix. And to do a classification or regression, we need the notion of distances or divergences, for example, between them. And it has been found that the Euclidean distance between them tends to be suboptimal. So there's a lot of work in the literature trying to exploit the geometrical structures, the non-Euclidean geometrical structures of these objects, the Gaussian measures and SPD matrices. And so I was involved when I was in Italy in the group of Vittorio. I was actually involved in doing this for the for computer vision applications using SPD matrices with the covariance representation of images, and with the generalization to the infinite dimensional setting, actually starting from. So this line of work really kind of started with the work that I was doing in Genova with Vittorio with IIT. A while ago, actually, but at the time it was really application oriented, and since coming to Japan, it has become a lot more systematic. So actually, I have a line of work. This is actually a line of work starting really from that point, but it has become a lot more kind of theoretically oriented since coming to Japan. Okay, so this anyway, so this is actually the motivation for the original motivation for the mathematical study, but. The work in the literature, mostly, there's a lot of work in the literature on the finite dimensional setting of Gaussian measures and SPD matrices. My focus is really on the infinite dimensional setting. So first, I will give a brief review of the Fisher-Rao metric and on the set of Gaussian densities on Rn and the corresponding Riemannian metric on the set of SPD matrices of the so-called affine variant Riemannian metric. from the setup, so I'm just focusing on the setup center Gaussian density, so kind of zero mean Gaussian densities. So it's given by, so we have this formula here. We have this. So the probability density is given. The Gaussian density is given given by this formula. It has an explicit form, and it depends entirely on the covariance matrix sigma here. And so it can be. So it's basically corresponds to the set of SPD matrices and given by it parameterized by a set of parameters, where this parameter set here belongs to the r to the power k, where k is equal to nn plus 1 over 2 because we have the symmetry. And so we can define the classical object on the Fisher information matrix. And so it's given by this formula here. And when this matrix is positive definite, it defines a Riemannian metric on this set S. And so called the Fisher-Rao metric or Fisher information matrix. This is a very classical object in information geometry. It's a very, it dates like from more than 100 years ago. And so the Fisher-Rao metric is a central object in information geometry. And in the case of the Gaussian density, we actually have a closed form formula. And because of the correspondence between the set of Gaussian densities on Rn and the set of SPD matrices, we have the corresponding Riemannian metric on the set of SPD matrices. It's called the phi invariant Riemannian metric. So it's given by this explicit form. So this is the kind of the inner product between two matrices A and B, which is in the tangent space at the point sigma, where sigma is in the SPD matrix. So it's given by, it has a closed form formula. So this matrix has been studied extensively in the mathematical literature. It actually dates from a long time ago. I'm giving some references, but it's actually, it dates from as far as I can tell from the 1940s. So with this Riemannian metric, the set of SPD matrices becomes a Riemannian manifold. It has that's a unique geodesic joining any two matrices A and B as given by this closed form formula. Starting from A ending in B, and we have a closed form formula for the geodesic distance given by this formula here. So we have a very rich mathematical structures and corresponding to the Fisher-Rao distance between zero mean Gaussian densities on Rn. So it has been studied a lot mathematically, and it has been applied a lot in applications as well. For example, also in computer vision, and also in brain-computer interfaces in BCI. Well, Tomek is not here, but actually Tomek really would like to apply to BCI. And also actually we did some work in this with Luca Dodero back then using some of these metrics. So now my focus is really on the infinite dimensional setting. There was a finite dimensional background. I'm talking about the infinite dimensional setting. So here we're talking about the setup positive Hilbert-Schmidt operators on a Hilbert space. So this is the generalization of the Frobenius inner product on a Hilbert space. So the inner product between A and B is given. It's actually the same formula trace of the adjoint of A or the transpose of A with B, except that we just have infinitely many terms, and for any orthonormal basis EK. And the set of Hilbert-Schmidt operators, just a set of operators, bounded operators, so that this norm is less than infinity. And especially for the set of symmetric or self-adjoint Hilbert-Schmidt operator, then this norm square is just given the summation of all the eigenvalues square. So it's just a generalization of the Frobenius inner product. For the finite dimensional case, we just have the summation of all the finite, the sum square of all the eigenvalues. And the Chase class operator is for the infinite dimensional set, the Chase class operator will be a subset of this set, and it's where the Chase norm is less than infinity. So for self-adjoint operator, the Chase norm is just equal to the summation of all the eigenvalue, absolute value, and the Chase is equal to the summation of all the eigenvalue. So this one is like an L1 norm, and this is an L2 norm. So for the Euclidean space, the Gaussian measures correspond to the set of positive semi-definite matrices, and for the non-degenerate Gaussian measures, which has density, then they correspond to the set of SPD matrices. So on a Hilbert space, we have a similar thing. We just have the correspondence between positive Chase class operator and positive, kind of strictly positive Chase class operator for the non-degenerate Gaussian measures. So because of this correspondence between the set of Gaussian measures and positive Chase class operators, we have the geometry of the Gaussian measures very correspond to the geometry of the positive Chase class operator. But for the Riemannian metric, it's actually necessary to consider the larger set of positive Hilbert-Schmidt operator. Remember that in the infinite dimensional setting, this set will be larger because it's an L2 norm, this is an L1 norm. It's not, for the Riemannian metric, it's not necessary to consider this bigger set. So one of the challenges of doing this generalization. Now remember that in the finite dimensional setting we have these formulas here. We have this formula of the geodesic and the Riemannian distance here. We need to take the inverse of A and we need to take the log. So we need to do these operations. Then we're going to generalize it. Now, so the challenge is that when we generalize it, when A is positive Hilbert-Smith operators, it has an infinitely many eigenvalues. And we have the spectral decomposition here. So the eigenvalues will go to 0 when K goes to infinity. This is actually for any compact operator. And so because the eigenvalue goes to 0 when K goes to infinity, we have the log of lambda K will go to negative infinity. So A inverse will be unbounded and log of A will be unbounded because this will just go to negative infinity, is go to infinity. So this formula here generally is unbounded. No, it can be bounded, but only under certain assumptions. And so the result, so the previous formula cannot be generalized directly to this in this setting. So the solution is the resolution is to do regularization. So for example, so we just add like a term of gamma I where I is the identity operator, so we can A plus gamma I, and with gamma greater than 0, then this operator becomes strictly positive definite, and then we can do the inverse, we can do the log. So these operators are bounded. So now we can take the log, and this log is bounded because of this regularization. Now in the mathematical literature, this is not called regularization, it's actually called unitization because you're adding a unit to it. But it corresponds really to regularization actually in the context of inverse problems of machine learning. So now this log is bounded, but what do we do here? Because if we take the Hilbert-Smith norm, then this is actually generally equal to infinity when gamma is not equal to mu. And so, because the identity operator is actually not Hilbert-Smith, so this norm is generally equal to infinity. So what we can resolve is that we do something called the extended Hilbert or extended unitized Hilbert-Smith operator. So we add a term A plus gamma I as before, and we have to introduce something called the extended Hilbert-Smith or inner product and extended Hilbert-Smith norm, so that the identity operator and the Hilbert-Smith operators are orthogonal to each other. And we have, so then the norm is given by this formula here. And so the norm of the identity operator is actually equal to 1 instead of equal to infinity. And we can study this set of positive definite operators. And now this is now a Hilbert manifold. It's an subset of the Hilbert space, and so an infinite dimensional manifold. And we can generalize the affine invariant Riemannian metric on this set. So it's given by this formula here. So it's actually very similar to the infinite finite dimensional setting, except that we do this regularization or unitization everywhere. And under this metric, we have an infinite dimensional Riemannian manifold. That's a unique geodesic joining every pair of A and B. And we have the Riemannian distance. So we have a closed form formula. So everything can be generalized from the finite dimensional setting, except that we do this regularization. And then we use this extended Hilbert-Smith norm. So, so inspired by this formulation, we can actually do this also for the infinite dimensional divergences. So we have a lot of divergences on the set of SPD matrices. We have the log-net divergences correspond to the unit divergence on the Gaussian densities on our end. So they are given by this family formula here, parameterized by a parameter alpha. So this one, when alpha equal to 1 corresponds to the K-on, the Kubic library or K-on divergence. So these are also not, in general, not unbounded because this is unbounded, and the chess is also not well defined. So just very briefly, we can also do in a very similar way to generalize this. We can actually generalize all of these formulas to the infinite dimensional setting by doing regularization and doing the kind of extending the definition of the traits. So here we have similar to the extended Hilbert-Smith norm, we have the extended traits, and we can also try to extend the definition of the determinant. We have something called the extended Fredholm determinant. So, and then we can have a formula we can generalize the log-net divergence using this formula. So this is actually a simplified version because the general formulation is actually more complicated. So everything, so we just replace A by A plus gamma I, B by gamma I, and then we do the extended determinant instead of just a regular determinant. And these are all finite, and they can be shown to be valid divergences. And so in the case, now, in the infinite dimensional setting, the Gaussian measures are actually very, the behavior in a very different way compared to the finite dimensional setting. So in the finite dimensional setting, we have these Gaussian densities that we have the full support of all of the all the Euclidean space. In the infinite dimensional setting, they are either equivalent or they have the same support or they are mutually singular. So it's actually very different behavior. We can show, And then we have the S alpha log divergence, this is about the ring divergence. We can show the same thing in the infinite dimensional setting for equivalent Gaussian measures. So if we have two equivalent Gaussian measures, and then when this regularization parameter goes to 0, we will recover the exact Kubeck-Leibler or the Rayleigh divergences. So it involves something called the Hilbert-Gamma determinant. Okay, so it just so we can actually generalize all of the distance in all the divergences in the finite dimensional string by SPD matrix to the infinite dimensional string of positive definite operators by doing regularization, by extending the definition of the Hilbert-Schmidt norm or the trace and the determinant. So that it involves like it involves a series of kind of generalization, and we can actually do it in a very general setting. We can actually generalize it to the set of we can actually just have something called the alpha beta log divergences. So this formulation encompasses both the log alpha log divergence that I described just now and the affine invariant Riemannian distance. So it's actually a very general formula. So now I will be talking about the Fisher. So now we're talking about the Fisher metric now for the infinite dimensional Hilbert space. And before that, I was talking about the Fisher metric for the Gaussian densities on Rn. So now let's generalize it to the infinite dimensional setting using the concepts we were just talking about just now. So on Rn, one typically work with the probability density functions with respect to the Lebesgue measure. But there's no Lebesgue measures on the infinite dimensional Hilbert spaces, so there's no natural reference measure. So we cannot really talk about probability density functions. So we can consider a set of probability measures equivalent to a fixed measure mu0. So then the densities are, the Radon equilibrium densities are well defined and they're kind of strictly positive. So we can talk about the log and so on. So there's a lot of work in the literature. There's kind of a lot. Well, most work in the literature actually deals with the finite dimensional setting, but there exists work in the infinite dimensional setting using the Banach manifold and so on. But these are actually highly abstract. So I will just talk about the kind of the equivalent center Gaussian measures here. So some of this work actually kind of part of this actually appeared last year, and it was actually just accepted kind of like a couple of weeks ago actually in information geometry. So, and now we're talking about the equivalent Gaussian measures. So two Gaussian measures on the Hilbert space are equivalent if and only if we have the following. So they obey these conditions here. So this is actually very different from the finite dimensional setting. So if we shift the mean, for example, just a little bit, then they will become actually singular. And then where all the kind of the distance and divergence become infinity. So we have to actually be very careful with these conditions. And now then we can introduce a set. We can introduce, because of this condition here, this is like the way the covariance operators are related. So they can be related by this formula here. And so we can introduce a set, the set of Hilbert-Schmidt operator S, so that is I minus S equal to 0. And we can fix the measure mu0, and we can set a set of all Gaussian measure equivalent to this mu0. And so because of this relation here in this theorem, this is a classical theorem, we can consider the set of Gaussian measures parameterized by this operator S. This is the infinite dimensional manifold, and so we have an infinite dimensional Hilbert manifold. And okay, I want to skip these. We can define and we can also consider the set of corresponding covariance matrices and covariance operators. This set in here, and so it's just here. So, and we can also define a tangent space. It's given by this formula here. It's kind of complicated, but this is the formula for the tangent space of this set of Hilbert manifolds given by this set of Hilbert-Schmidt operator, except that we multiply and post multiply by C0 to the power half. And so what is the definition of the Fisher metric now? So before we take the logarithm of the infinite dimensional setting, we take the log and then the density, and then we take the derivative, and then we carry out the integration. Now so in the more general setting, we kind of do it in a general way, except that this is like the Fisher derivative at the point S along the direction V, so with the tangent vector. And where we d mu0 is now the Radon equilibrium density of mu with respect to mu0. So now this formula, of course, is only well defined if this is differentiable and this thing belongs to L2, so it can be integrable. And we can do it actually. We can do it in this setting in this Gaussian setting. So I'm just showing you the formula here to show you that we can actually have an explicit form, and then we can do you don't have to worry about these details, but we can actually do it. We have this is a closed form formula for the Fisher, for the Radon-Nikodym density and the derivative here. The logarithmic derivative of the Radon-Nikodym densities. And then we can take in the case when V is the Chase class and also S is Chase class. And in the other cases, you can take the limits in L2. Just to show you that we can actually do all this computation, and then we can compute this in the product here. So it's given by this formula. So this formula here will give us the Fisher-Rao metric in the infinite dimensional setting. Okay, so this is the Riemannian metric. This is I was talking about just now. This is the Fisher-Rao metric for the on the set of Gaussian measure equivalent to the Gaussian measure mu0, and we have the corresponding Riemannian metric on the set of the corresponding set of covariance operators. So it has the same formula as in the finite dimensional setting. It has the same formula. Because in this case, everything is well-defined. Now, in general, this is not well-defined, it's unbounded, but in this particular set, we consider this particular set. So in this set, these are all bounded and well-defined. And we can compute everything corresponding to this, all the Riemannian structures when actually have closed forms. So we can compute the Levi-Civita connection. We can compute the Riemannian curvature tensor. It has a closed form formula. So we just have to be very careful that these formulas are finite dimensional setting, because not everything in the finite, everything is finite, because not everything from the finite dimensional setting will remain bounded in the infinite dimensional setting. And so we can compute the sectional curvature as well. This is less than or equal to 0. So we have the manifold, which has non-positive sectional curvature everywhere. So actually it has the same, basically in this setting, we actually generalize everything from the finite dimensional setting. So remember that this is only possible when the Gaussian measures are equivalent. And we also have a closed form formula for the geodesic, and the geodesic distance. So this is kind of the Riemannian distance between A and B. It's given by this formula here. And we have the connection with the Riemannian geometry positive definite Hilbert-Schmidt operators, because remember before we have this formula for the geodesic distance, and this is the distance for the Gaussian measure, equivalent Gaussian measures. So this formula on the left-hand side here can be considered as a regularized version of this formula on the right-hand side. And on the left-hand side, we can actually do the finite dimensional approximation, for example. So the left-hand side, for computational purposes, is actually a lot more important, because this formula on the right-hand side here has closed form formula, but of course it's an abstract formula, so it's not so easy to compute. So now. Okay, with some minutes remaining, I would like to talk about this Gaussian process setting, because so before we were talking about the Hilbert space setting with the Gaussian measures. Now these are all abstract formulas, and it's not clear. Of course, in general, it's actually very difficult to compute all the distances and so on. So let's talk about the setting where we have the Gaussian within Gaussian processes. So the Gaussian process with probably with mean function M and covariance function K. So if we assume that assuming that the sample pairs are square integrable, so this happens if only we have the mean is square integrable and we have this covariance function satisfying this condition here. So this basically this covariance function KST here is positive definite kernel actually. So we have a one-to-one correspondence between the Gaussian process and the Gaussian measures on the Hilbert space L2, where we could have square integrable functions on an interval T, where suppose T is a compact interval from 0 to 1, for example, and nu can be the Lebesgue measure, where CK is the integral operator given by this kernel function KST here. So these are the examples of the Gaussian process here. So this is the Gaussian process sample of the Gaussian processes with covariance function K1, which is the Laplacian kernel. So it's on the left hand side here. On the right hand side, we have the Gaussian processes correspond with the kernel function given by the Gaussian kernel. So it's a lot smoother for the Gaussian kernel, of course. And so these are the kind of the sample pairs generated by these Gaussian processes. So they are square integrable from the interval from 0 to 1, with these interval from 0 to 1. And so they are induced by Gaussian measures on the Hilbert space L2 from the interval 0 to 1 with the Lebesgue measure. So we can actually compute the distance between them. So there's a lot of work in the literature actually computing, studying the distance and divergence between Gaussian processes, and a lot of work in functional data analysis using the Hilbert-Schmidt distance, which is not really optimal. There's also work in the Wasserstein distance, and so using the Wasserstein distance in the context of functional Bayesian neural networks. So actually, people kind of study the K-on divergence, for example, in the context of functional Bayesian neural networks. But it's actually very difficult to compute the sample complexity of this K-on divergence. Recently, there's work in machine learning on studying whether K-on divergence is replaced by the Wasserstein distance. But of course, if we want to do like gradient descent using the Wasserstein distance, it's not well defined because the Wasserstein distance is not differentiable in the infinite dimensional setting. So now we can, in general, this actually infinite dimensional setting is actually very difficult to compute, but what we can do is you can compute the finite dimensional approximation. And so we can sample like a set of points on this interval from T here, and then this we have like a set of vectors that have a Gaussian distributed by Gaussian measure with covariance matrix given by the Gram matrix corresponding to the kernel. And so we can show that we can estimate the infinite dimensional formula using the finite dimensional of the Gaussian measures in the infinite dimensional Hilbert space by the finite dimensional Gaussian measures in RM with this covariance matrices K1 and K2. And so this analysis actually makes extensively use of reproducing kernel Hilbert space methodology. I'm not showing it here, but it can. So this is actually this is the result here. So we can show that this is the finite dimensional. This is the infinite dimensional formula. So this shows that the infinite dimensional formula can be estimated by the finite dimensional formula, and this is dimension independent. It only depends on kappa here, where kappa is basically the size of the kernel, kind of the upper bound for the kernel, and depending on the sample size. Okay. So now I would skip the optimal transport because it's not. I'm sorry. I know. I started 1 minute late. So just so you know, and I'm not talking about the optimal transport. Basically, we have a similar story. We have closed some formulas for everything. So I'm just talking. So this is like kind of the distance between these two kind of Gaussian processes I was talking about just now. And so we have this kind of the talking about the phi. This is kind of the the distance here. This is the phi remaining distance. This is when we have the number of sample paths from 10 to 1,000. And this is the same thing. So in this case, these two Gaussian processes are much closer to each other because they are induced by the Laplacian kernel, except for with different parameters. So they are much closer. So the distance will be smaller in this case. Actually, they are larger because they are smaller. So anyway, so I'm skipping the optimal transport, but basically we can actually do a lot of things along pretty similar way using for the optimal transport. We don't need regularization to define the distance, but the okay, so I'm going to summarize the Fisher-Rao metric first. So we can actually generalize the Fisher-Rao metric and the distance divergences between Gaussian measures from Rn to the Hilbert space setting. Now we can only consider the equivalent Gaussian measures. In constructing the finite dimensional system, we can only consider equivalent Gaussian measures for this Fisher-Rao metric and also for the distance and divergences. Otherwise, they are actually equal to infinity. And for the kind of the log divergences between the positive definite operators, regularization is theoretically necessary for the finite dimensional formula for the finite formulation to have like a finite results. And we can show that by doing regularization, we can have finite distance between any pair of Gaussian measures, and we have dimension independent sample complexities. Now we can actually, I didn't talk about the optimal transport. Now for the Wasserstein distance, everything is actually well defined. But when we do the regularization using something called the entropic regularization, we can also obtain like the sample complexity. We have also many nice results. So regularization is a very important thing. This is kind of the key message here is that when we do regularization, we obtain many nice properties. So of course, there's many theoretical results can be obtained. Actually, I have a long line of work along this for this. And so we can talk about I'm trying to consider something called the infinite dimensional Hellinger-Cantor-Robrich distance, connecting information geometry and optimal transport, and generalizing to the quantum setting. So kind of this is a list of references. Okay, I'm open for comments, questions, suggestions, and criticisms. Thank you very much for listening.
We have no time, but we have time for one quick question if someone can comment or.
on page 41 in the results, you
41?
said that 41.
Just a second.
In the theorem for exclusion bond, you said that the result is dimension independent, but
well, yeah, it depends on this kappa. So the kappa,
kappa includes dimension, right?
Well, it depends. Like for the if you have the Gaussian, for example, then if you have the Gaussian, then kappa is equal to 1 actually. So it depends. So kappa, if kappa is an absolute constant, then it's completely dimension independent. It depends. Yeah, it depends on kappa. So kappa is like the kind of the like the size of the kernel, like kx1, xy less than or equal to kappa squared, basically. So for the exponential kernel, this is equal to 1 actually. Yeah, it's because of the regularization. We actually for the if we do the sample capacity for the Wasserstein distance, we will not get this behavior. But if you do it for the synchron divergence, which is the entropic regularization, we wouldn't get this. Now it depends on this gamma. You know this gamma here. So if this gamma goes to infinity, if I go to 0, for example, this will blow up. So it depends. So it's a regularization, but it depends on this gamma. So that's the catch. It's not free, because when we get closer to the real formulation, this would actually. It's actually the same behavior for the entropic regularization. We have this like epsilon for the entropic regularization. So the epsilon goes to 0, then we kind of the behavior will just blow up, because it becomes it becomes infinity. So eventually we still have it's still correct, but it's not meaningful anymore because it's less than or equal to infinity. So it doesn't say anything. Yuka is equal to 0.
Okay, so thanks, Minh. Let's thank the speaker.
Thank you very much.
My name is Yuka Hashimoto, and I'm a researcher at NTT, Japanese telecommunication company. And I'm also a visiting researcher at RIKEN AIP. So today I'd like to talk about deep learning with kernels through RKHM and Perron-Frobenius operators. So the RKHM, so here this RKHM is a generalization of reproducing kernel Hilbert space, RKHS, so by means of a notion called sister algebra. So we first explain the motivation and background, and then we introduce what is reproducing kernel Hilbert sister module, RKHM, and then we consider the deep setting of RKHM. So first, let me begin with the background. So kernel methods have been actively researched, and in this setting, there is a sample, and we transform a sample into a complex varied scalar varied function by using a map called the feature map. And in many cases, the original data space is finite dimensional space, but RKHS is composed of these scalar varied functions, and it is in general infinite dimensional space. So the nonlinear behavior in the original space is transformed into a linear one. It is lifted up to a high dimensional or infinite dimensional space and becomes a linear behavior. And by using this feature, we can implement some classical algorithm like principal component analysis or support vector machine on RKHS. And we can also use RKHS to run complex scalar valued functions because RKHS are complex valued function spaces. And advantages of RKHS include, as I said, nonlinearity in the original space is transformed into a linear one, and also in more practical view, from more practical point, we can compute inner products in RKHS exactly by computers. Yeah, and this is a definition of RKHS. So we quickly review the definition. Let X be a set of for data, and we consider a map, two variable map, and the scalar variable map K. It is called a positive definite kernel. It has two properties. These properties corresponds to the property of inner products. The first one corresponds to the symmetricity, and the second one corresponds to the positive definiteness. And we define a map called the feature map by fixing the second variable of K. And we consider the space spanned by these feature maps. And then we can define an inner product in this space by using the positive definite kernel defined here. And RKHS, it's defined by using this space and the inner product. And an important property in the RKHS is that it's reproducing property. So if we consider the inner product between this feature map of phi of x and phi, where b is in the RKHS, then we can reproduce the value of b at x. So by virtue of this property, we can write exactly the algorithm in the computers. Yeah, and the goal of our research is to generalize data analysis in RKHS to RKHMs, which is a generalization of RKHS. So in the framework of RKHM, we transform a sample into a sister algebra varied function. So sister algebra is a generalization of complex values, and important examples include functions and operators. I will explain in more detail in the next slides, but here we are considering something like function varied function or operator varied function. And also in RKHM, we can make use of sister algebra varied inner product instead of the scalar varied inner product. So the advantage of RKHM includes we can make use of sister algebra varied inner products but to extract information of structures of data. So if the original data has structures such as functional data or image data, then we can make use of sister algebra varied inner products to extract these structures. And we have been working on this, working on RKHMs, and we showed RKHM is a natural generalization of existing RKHS. And also we have shown some fundamental properties for data analysis in RKHMs, such as representer theorem or kernel mean embeddings. Let me briefly explain what is sister algebra. So sister algebra is a space equipped with a norm and product and an involution. Important examples are the space of continuous functions on a compact space. So in this case, the norm is the supremum norm, and the product is the pointwise product, and the involution is the pointwise complex conjugate. And also, another important example is the space of bounded operators on bounded linear operators on a Hilbert space. In this case, the norm is the operator norm, and the product is the composition of two operators, so the product of two operators, and the involution corresponds to the adjoint of the operator. So basically, we are considering functions or operators in this framework. So before going into the technical details of RKHM, we discuss advantages of RKHM. So first, we can enlarge representation spaces using sister algebra compared to RKHS. So if we have to, and also we can design sister algebras to obtain appropriate RKHM. So for example, if we have two sister algebras and A1 sister algebras A1 and A2, and if A1 is smaller than A2, then the corresponding RKHM with respect to A1 is smaller than the RKHM over A2. So we can design the representation space by properly choosing the sister algebra. And secondly, we can make use the product structure of the sister algebra. And for example, many positive definite kernels involve product structures. So for example, polynomial kernels are defined by using the products. So we can naturally generalize the polynomial kernel by using the product structure of the sister algebra. And the product structure of the sister algebra is more complicated than in the case of the complex values or real values. So we can make use of these properties of product structures. And finally,
in the picture, the x is the little x. The x is an element of the data set, but here you're multiplying it and saying they're elements of the algebras.
Yes. Yes. Sorry. This is in the case of x equals the sister algebra.
Okay.
Thank you. And finally, we can use the operator norm. So because we are considering operator sister algebras are the space of operators, we can make use of the operator norm to alleviate the dependency of the error bound on data dimension. So I will explain it later. And let me review what is RKHM. So let A be a sister algebra. So RKHS, in the case of RKHS, we considered complex valued, scalar valued positive definite kernel. And also RKHS are composed of complex valued functions, and it is equipped with complex valued inner product. But in the case of RKHM, we consider A valued sister algebra valued positive definite kernel, and sister algebra valued, it is composed of sister algebra valued functions. And also it is equipped with a sister algebra valued inner product. So let me skip this slide. But the definition is the similar as the case of the RKHS, but we are considering the A-valued positive definite kernels and A-valued inner products. So in this work, we try to generalize our formulation in RKHM to the deep setting. So in existing works, combining the flexibility of deep neural networks with the representation power and the solid theoretical understanding of kernel methods have been investigated. So in this framework, in existing frameworks, we consider RKHS, an especially vector-valued version of the RKHS. So in this framework, we consider a vector input, And then we consider multiple RKHS, H1, H2, H3, and so on. And then we transform the input vector into another vector by using the function in the RKHS. And we continue that by using the functions in the RKHS. And then we finally get a vector output. And this formulation is represented by using the composition of the functions in the RKHS like this. And we call it deep RKHS. And we want to generalize it to RKHM. And before introducing deep RKHM, deep version of the RKHM, we introduce a notion of Perron-Frobenius operator, so which is a very useful tool for explaining the composition structure. So let F be a nonlinear map, and the Perron-Frobenius operator is defined by using the feature map of the RKHS or RKHM, and it describes the composition of with the function f. So by using these Perron-Frobenius operators, we can use the composition structure. We can represent the composition structure of the deep RKHS or deep RKHM. And yeah, now we define deep RKHM. So we focus on the sister algebra of matrices, D times D matrices. And in our framework, we consider a matrix varied input. And then we consider multiple RKHMs, M1, M2, and so on. And then we transform the matrix varied input into a block diagonal matrix varied, block diagonal matrix. Block diagonal matrix is the sub algebra of the sister algebra of D times D matrices. So this is also a sister an element in the sister algebra. So we transform a sister algebra into a sister algebra, and by using the function in the RKHM, and we continue that, and then we finally get the output of, which is also in the space of matrices. So in the case of deep RKHS, we consider that we transform the vectors. We consider vectors, but in our case, we consider matrices, and the dimension of the vector here corresponds to the number of elements in these matrices. And by using the reproducing property and the Perron-Frobenius operator, we can represent the deep RKHM like this by using the inner product and the Perron-Frobenius operators like this. And by using this representation, we showed a generalization bound. And this is the generalization bound. And this is a very, this looks like a very standard generalization bound for kernel methods. But the difference is we use the operator norm here. So because we are considering RKHM and the output is the matrix varied, so we need some norms to measure the operators. So we use the operator norm here. And we use the Perron-Frobenius operators and the inner product to represent the deep RKHM. And then we have the constant here, and this is explained by the norms of the Perron-Frobenius operators. And we can let me explain what is the difference between our bound with the typical existing bounds. So in our case, we considered the matrix input and the matrix varied output, and we can also use the we can also flatten the matrix, this matrix to a very long vector. So we can consider D by D matrix, but we can also consider the D squared flattened version of the long vector. And then we can use the vector valued RKHS, vector version of the RKHS to represent D squared dimensional vector valued functions. But in this case, the typical generalization bound is like this. So in this case, because we are considering D squared dimensional vector, so we have another dependency of D here. So this is because if we consider D squared dimensional vector, then the norm of the D squared dimensional vector basically depends on D squared. But in our case, we are considering the matrices, and in that case, we can consider the operator norm, and the operator norm basically depends on the dimension D. So we can alleviate the dependency of the generalization bound here on the output dimension D. And by using this generalization bound, we can formulate the learning program like equation number 11 like this. So the first term is the standard error function, but we use the operator norm here. And the second and the third term is the regularization term. And this term is a unique regularization term of our formulation in the formulation of using the Perron-Frobenius operators. So this comes from this constant described by the norm of the Perron-Frobenius operators. And about this minimization program, we have a representer theorem. So this representer theorem shows the solution of this minimization program is described only by using the input and output training data. And the unique part of our formulation is here, this regularization term. So we evaluate this regularization term. So this is upper bounded by using the gram matrices of the kernel, of the training data. So, and we can bound it like this. So it involves the inverse of the gram matrix and the standard gram matrix. So to reduce this value, we can reduce this value. And reducing this value corresponds to trying to get the largest and the smallest eigenvalues of the gram matrix closer. And we have an existing theory about the overfitting for kernel regression. And according to that theory, deep RKHM appreciates the benign overfitting. And this, in the existing theory, they discuss the overfitting by using the eigenvalues of the gram matrices. And in our case, it corresponds to benign overfitting. And benign overfitting is the phenomenon that networks predict well even with a perfect fit to noisy training data. So both the training and test loss decreases in benign overfitting. Now finally, we show some numerical results. we considered classification task with MNIST. We considered the case where the training data is very small. So the size of the training data is very small. And in that case, deep RKHM overperformed CNN, convolutional neural network. And also, this is the training loss, and this is the test loss. And lambda 1 here is describes the, this regularization term. So lambda 1 equals to 1 corresponds to the case with the Perron-Frobenius regularization, and lambda 1 equals to 0 corresponds to the case without the Perron-Frobenius regularization. So with the Perron-Frobenius regularization, both the training loss and test loss decreases. For the test loss, it is not so big, but compared with the case without the regularization, the test loss becomes smaller, and training loss is also decreases. So in conclusion, RKHM, we considered RKHM. It is a natural generalization of RKHM, and RKHS, and we can deal with functions and operators because since the algebras are the space of functions and operators. And we propose deep RKHM, and it is constructed by the composition of RKHMs. And we applied Perron-Frobenius operators to represent the deep RKHM and used the operator norm to derive a generalization bound, and then the dependency of the error bound on the output dimension is alleviated. Thank you for listening.
Couple of minutes for questions, please, Minh.
Thank you for the beautiful talk. I would like to go to page, can you go to page 13? So here we have the generalization bound depending on the trace. So this K1 here is an A star kind of valued kernel, right? This K1 xi here belongs to A star, right?
Yeah, this is operator varied.
Yes,
sorry, this is a matrix varied.
Okay, so in this case, actually it's for finite dimensional setting, right? Because the trace here, if we have like an operator on an infinite dimensional space, for example, then we have to be very careful about the trace.
Yeah.
So this one is actually for the finite dimensional setting.
Yes,
Actually, so A star is actually finite dimensional. Okay.
Yes.
Okay, that's my main comment actually. But I think it's very beautiful. I think the whole framework is very beautiful. Thank you very much.
Thank you.
Thank you. Other questions? Matteo?
There's a question from Matteo.
Yeah.
Nice work. Mine is just curiosity in a certain sense. Effectively, you also are reducing the number of layers compared. I am interested on the last slide when you show that you are comparing with CNN, but you are also reducing the number of layers. Pretty much, you are using the level pretty much.
Yeah, thank you for the question. I think compared to the standard neural networks, we can reduce the number of layers because RKHM itself has very, very strong representation power. So even with one layer or 2 layers, it can represent very many functions. Yeah, but I'm not sure if I'm not sure compared to deep RKHS, our formulation deep RKHM can reduce the number of layers.
Okay, so let's go to next talk and the final talk.
Okay, thank you for introduction and thank you for invitation. I'm Sho, belonging to deep learning theory team, and today I'm mainly working on approximation theory perspective of deep learning. Okay, let's start. So what is the typical solution obtained by deep learning? This is a big question I'm working for many years. And because deep neural network is a black box, we want to turn a black box into white box by clarifying how, for example, the network process information inside a network, in particular after the learning process. Right? And one approach I use is the Ridgelet transform. This is the main topic today. And to investigate in a information processing, how to process information, I formulate a problem as an equation defined by neural network. Okay, say given a data generating function f, this is an arbitrary function f on x. Find a parameter gamma of DNN satisfying DNN of gamma equal f. And we call the solution operator R to this equation. I call it Ridgelet transform. Okay, so in the first half of my talk, I will introduce Ridgelet transform for depth to fully connected neural network on a Euclidean space. This is a classic version of Ridgelet transform. And then I will introduce our latest results. This is a Ridgelet transform for deep depth N or deep neural network. Okay, let's start. So first I introduce shallow neural network. Of course, you are sure about shallow neural network, but just for introduction. So it is a function of x parameterized, and the parameter is a and b and c, and here sigma is a nonlinear activation function, and it is fixed. And typically sigma is a ReLU or Gaussian or hyperbolic tangent. And to understand this function geometrically, here I put a figure of illustration graph of a single hidden neuron. And in the case of activation function is a Gaussian, then it typically have a ridge shape, because inside a nonlinear function there is an inner product. So in the direction of x orthogonal to this parameter a, it will be a constant function, and it will be visualized as a constant direction in the graph. So before step inside mathematical detail, I will introduce intuitive understanding how neural network approximation function. This is simply by drawing many lines in the screen. So because I said that sigma a dot x minus b, this corresponds to a ridge on the screen. So, and this is an artwork produced by an Italian artist and made by pins and threads. And so you can, of course, see the face of Christ, right? And this is made by drawing many lines on the two-dimensional screen. So if you draw if you draw two lines, then you can make a cross point. And if you make a dense part by gathering crossing points, you can make a dark area. And if you avoid making cross points, you can make a whiter, brighter area. So by controlling and dense and bright area, you can draw an arbitrary two-dimensional signal on two-dimensional space, right? This is an essential mechanism how neural network approximate an arbitrary function on two-dimensional space. And this mechanism can be applied for an arbitrary dimensional space. So, in this sense, we can understand A controls the width of ridge, and B controls the location of ridge, and C controls the height of ridge. And yes, this is an essential understanding. So, okay, And the Ridgelet transform is an integral transform that can automatically compute what A and B and C. So to introduce a Ridgelet transform, I will explain integral representation of neural network. This is a mathematically convenient formulation of a neural network, single hidden layer neural network. And the upper panel corresponds to a finite width neural network. And the bottom panel corresponds to infinite width neural network, which I call it integral representation. So here, sigma A dot x minus b corresponds to integral kernel. And in this infinite width setup, all the possible hidden parameter A and B are integrated. So in this setup, we do not need to choose which A and B to use. Instead, we control which A and B to use by weighting on them. So in this infinite dimensional setup, this gamma will be the only linear parameter. So this is a mathematical trick because inside sigma, this AI and BI is nonlinear, and this makes the analysis of neural network parameter difficult. But in this continuous setup, this gamma is in the place of a linear parameter. So linear means that if you twice this gamma, then the network itself will be twice, right? This is a mathematical trick. And the Ridgelet transform is defined by an integral transform of a function to be approximated f, to be approximated, and the rho a dot x minus b. Here, rho can be different from activation function sigma. And what happens here is that if we substitute this Ridgelet transform with the place of weighting function gamma, then this continuous neural network can reproduce the original function f. And because this reconstruction formula holds for an arbitrary square integrable function, this means that the continuous neural network can reproduce or approximate an arbitrary square integrable function. Okay, and we can also understand this as a parallel of Fourier and the inverse Fourier transform. I mean, because this Ridgelet transform R of f corresponds to a weighting function on some integral kernel. This relation corresponds to a Fourier transform and the inverse Fourier transform. Makes sense. And this is a visualization of a Ridgelet transform. So for the purpose of visualization, I pick up a one-dimensional signal case, and this is a truncated sinusoidal curve. Then we can compute the Ridgelet transform by using a numerical integration, and this is here the left panel corresponds to an original function, and the right panel corresponds to the result of a Ridgelet transformation. And here, red part corresponds to positively high intensity f, and blue part corresponds to a negatively high intensity. So typically, the result of weighting function is oscillating. And this is a reconstruction result. When sigma and rho, the coupling condition of sigma and rho is not orthogonal to each other, then by computing the integral representation with Ridgelet transform R of f, then it reproduces the original function f. And when this sigma and rho are orthogonal, even though the Ridgelet transformation has some information of original function f, it degenerates to a zero function. Yeah. And one nice thing is why Ridgelet transform is happy is that after After learning a finite width neural network by using gradient descent, they typically converge to the distribution of parameters converge to the Ridgelet transform. So in this sense, the Ridgelet transform can explain how neural network parameters are acquired. Okay. And because this is how Ridgelet transform looks like for the traditional case. But the Ridgelet transform was originally known only for the depth to fully connected neural network case. But in the deep learning age, we have a variety of deep neural network, like a convolution network or neural network or manifold or graph neural network. So for our last few years, we are working on developing a method to find a new Ridgelet transform for an arbitrary neural networks. And we developed two ways of methods. One is by Fourier expression, and the other is by a group equivariant functions. And today I want to introduce the result, a new method of ours by using a group equivariant functions. This is a very fresh result. So, how to find the Ridgelet transform for deep neural network case? So in particular, this is almost the first Ridgelet transform for deep neural network. And this is a joint work with Hashimoto-san, the previous speaker, and Ishikawa-san there, and Ikeda-san. Okay, let's move. Let's start. So I first introduce the joint G equivariant map. This is a generalized version of a well-known G equivariant map. Okay, let G be a group, and let X and Y and Xi be G spaces. A map phi of X parameterized by Xi and mapping to the data output space Y is, we say, joint G equivariant when it satisfies the function value phi of G dot X and G dot Xi. This is a simultaneous action of group G on data and the parameter simultaneously, and then the function value will be acted by group G. So we call it a joint. Here, joint emphasizes that the group also acts on the parameter space Xi. So in an ordinary setup, when feature map is group equivariance, we do not assume the group action on parameter space. But here we also assume the group action on parameter. This makes an analysis very easier. And of course, the joint G equivariance is a superclass of a group equivariance. All right. Why it is happy? Because we can find joint equivariant maps very easily. For example, you can create joint equivariant maps very systematically. Let G be a group and X, Y be G spaces, and take an arbitrary mapping from X to Y. This need not be joint equivariant map. And we can make the joint equivariant map by acting a group on this phi 0 by this equation. Then this phi generated by phi 0 and the group action is joint equivariant. This is essentially a regular action on X and induced action on the output space. This is very systematic. And in addition, if we combine this result with Ridgelet traditional old classical Ridgelet transform with for depth to fully connected network, you can make joint group equivariant depth to fully connected neural network, right? And thirdly, this is another nice property of a joint group equivariant map. Well, we can composite the joint equivariant maps. What does it mean? I mean, let the phi be joint equivariant maps, and if we combine or composite this phi n times, and then the composite is again a joint equivariant map. So this is essentially a deep feature map, right? And the main result is that here's the main result. Let G be a locally compact group. Here, locally compact group is assumed to use the Hall measure on G and X and Xi, parameter space Xi. And let X and Xi be G spaces with Hall measures. And let Y, this is a space of output vectors, be a separable Hilbert space with unitary G action. And let phi and psi be an arbitrary joint equivalent maps. And define a deep neural network as a weighted integration of a joint group equivalent function with respect to parameters. And let the Ridgelet transform be a weighted integration of a joint group equivalent function with respect to function f to be approximated by neural network. And the statement is that suppose this is almost essentially the only assumption. Suppose that the induced representation pi is irreducible. Then if we composite the DNN of R of f, then it reproduces an arbitrary, it can reproduce an arbitrary function, scale integral function f on X mapping to the vector space Y. So you can, it essentially says that you can approximate or you can reproduce an arbitrary scale integral function. Okay, and a nice thing is to use the group representation theory is that the proof is very short by virtue of the fundamental theorem of group representation theory known as the Sho's lemma. This is an abstract theorem, but it says that a unitary representation P of G on H is irreducible if and if any bounded operator T on H commutes with H. If any continuous operator T on H commutes with pi, then that T, that operator T, have to be a constant multiple of identity. This is a very abstract, but we use this theorem to the operator defined by the composition of DNN and R. And by the construction, we can show this commutation directly by using the group invariance of measure and group equivariance of feature maps. Okay. So by direct computation, we can show the pi and nn of R commutes. So according to the Sho's lemma, we can show that there exists a constant C that only depends on feature maps that such as nn of R is the constant multiple of identity. Okay. So the proof is very short. And we have two examples. One is the depth to fully connected neural network case. This is a traditional Ridgelet transform case, but in this case, the group is a nothing group, and on data space, it acts in a typical way, like Lx plus t, and in addition, it acts on a parameter space. I mean, the affine group acts parameter space. This is a bit technical, but looks weird. But with this dual G action, the feature map sigma a dot x minus b will be joint G invariant. So joint G invariant is a subcase of a joint G equivariant, right? And so according to the general result, if you define a neural network as a integration, weighted integration of sigma a dot x minus b with respect to parameters, and the Ridgelet transform as a weighted integration of a function f, then and because for the affine group case, we know that the regular representation is irreducible. So according to a general result, we can say that the NN of R is identity after constant. And finally, the depth and fully connected case. So because so using the general construction method from group equivariant function, we can prepare a neural network that is group equivariant with respect to affine group. And because the composition of a group equivariant maps, again, a group equivariant, so this feature map, this is essentially a deep part of a neural network. And this is exactly implemented by sigma blah blah stuff. So this is exactly deep neural network part. And let the DNN of gamma is a weighted function, weighted integration of a feature map with respect to parameters. And let the Ridgelet transform of f as a weighted integration of between with the function to be approximated and the feature map. Then because the group representation is irreducible, if we combine DNN of Rn, then it reproduces the original vector field, right? Vector valued function. So this is a corollary. Okay, in conclusion, the ultimate goal is to characterize the deep network solutions, and we have seen that the shallow solutions are characterized by Ridgelet transform, and we want to know how to derive Ridgelet transform for a more general setup. And today I introduce the method by using a joint equivariant functions. Okay, this is the end of my talk. Thank you very much.
Thank you. Questions?
Yeah.
So this constant C here.
Yeah.
So the statement said that there exists a constant C. Can be computed?
Can be what?
It can be like, do we know it explicitly, or is it is it a resistance result?
That's a good point. But by this construction, we cannot compute what C is. So we need to calculate more directly. Because we use a Schur's lemma. This is just an existential theorem.
Okay. But I think it's a very beautiful framework.
Thank you.
Thank you very much.
Thank you. Other questions? No more? Okay, so people would like to have a coffee, and yeah, thank you again.
Thank you very much.